Hello there. In this video we're going to discuss, to some people, a very clever substitution method that can be used when you have a function containing sines and cosines, which will allow it to transform into just an integral of rational functions only. The substitution is stated as follows. Namely, if you have an integral of a function containing both sines and cosines with respect to x, then this is equivalent to finding the integral by replacing sine with the function 2u over 1 plus u squared, replacing cosine with the function 1 minus u squared over 1 plus u squared, and replacing dx with the function 2 divided by 1 plus u squared du. Now at first, this substitution may not look so obvious, but we're going to describe simply how this substitution comes about and also work through an example to demonstrate how it works. Alright, so the main idea behind the Varistor substitution is almost like a clever form of trigonometric substitution. With the substitution, u is equal to the tangent of x divided by 2. So if this is the case, then if we solve this equation for x, it's pretty much like replacing x with 2 times the arc tangent of u, right? And then we can start to see how things sort of turn about. So if x is equal to 2 times the arctangent of u, then we clearly see that dx is going to be equal to 2 divided by 1 plus u squared, right? So we at least get the first piece of this puzzle. So what about the rest? Alright, so let's just recall just a couple things about trigonometry, right? So what is 1 plus u squared equal to? So this is the same as 1 plus tangent squared of x over 2. So by the Pythagorean identities, we know that this is the same as the secant squared of x over 2, right? So this is going to be a useful little algebraic trick that we're going to need. Also recall that the sine of 2t, using our double angle identities, is the same as 2 sine t cosine t, right? So if we replace t with, say, x over 2, then we get that the sine of 2 times x over 2, which is the same as, of course, just sine x, is going to be equal to 2 sine x over 2 cosine x over 2, right? Now, why do I want to do that? Well, it introduces these x over 2 things, right? So if that is the case, then that means this is going to be equal to 2 times, so the reciprocal of sine is going to be equal to cosecant. So you have cosecant of x over 2 times the reciprocal of cosine is going to be secant. So we have secant of x over 2 there, right? Now, why are we sort of going through this? Well, remember that the Weierstrass substitution replaces sine with a rational function and it replaces cosine with a rational function as well. All right, and we have a representation for the secant squared of x over 2. That's in terms of u, 1 plus u squared, right? So we can clearly see what to do here, right? We can take the square roots of both sides of this expression. So we get that the secant of x over 2 is just equal to the square root of 1 plus u squared. So that's no big deal. So we have times 1 over the square root of u squared plus 1. And I leave it to you to verify that 1 over cosecant is the same as u divided by the square root of u squared plus 1. Right? Using some trig tricks. So therefore, we can replace sine of x with 2u divided by, so square root times square root is the interior, so we have 1 plus u squared there. Right? So this is the transformation, so sine gets mapped to this rational function. Right? So that's the second piece of our puzzle. And similarly, you can verify that cosine of x is going to be mapped to the function 1 minus u squared over 1 plus u squared. Right? So this is going to be the last piece of the puzzle. Right? So with all these things said, oh, and also let's recall, dx is going to be mapped to 2 divided by 1 plus u squared du. Right? So these things together, which originated from the substitution, u is equal to tangent of x over 2 is the Weierstrass substitution. So let's go through an example to sort of see how this would work. Alright, so the integral that I'm going to use to sort of demonstrate this is going to be the integral from 0 to 2 pi of the sine of x divided by 2 plus the sine of x dx. Now you may be able to use another method for integration for this outside the Varistor substitution, but I want to sort of illustrate how this sort of goes, and you can check it with other methods if you want. So what signals that I can use the Varistor substitution method here? So I only have sines and cosines in this integrand, so that's pretty much the only thing that you need. So again, the Varistor substitution uses the method u is equal to the tangent of x over 2. So remember that the tangent function does have singularities or vertical asymptotes at, for example, x cannot be equal to pi, 3 pi, minus pi, and so on. More generally, x cannot be equal to 2k plus 1 pi, where k is an integer, right? And notice that our interval of integration is from 0 to 2 pi. Therefore, we need to sort of dance around the singularity in the middle by splitting this integral up into two parts, right? So more in particular, we need to rewrite this as the integral from 0 to pi plus the integral from pi to 2 pi of the function sine of x over 2 plus sine of x dx, right? Alright, so let's use our Varistor substitution. So remember that sine of x is going to be mapped to 2u over 1 plus u squared, and dx is going to be mapped to 2 divided by 1 plus u squared du. And we've already proven those things before. So now let's focus on our limits of integration. Right? So when x is equal to 0, we know u is going to be equal to the tangent of 0 divided by 2, which is going to be equal to 0. So that's no big deal. So when x is equal to pi from the left, we know u is going to be equal to the tangent of pi from the left divided by 2. And as we know, as x approaches pi from the left of tangent, this goes to positive infinity. Looking at our other side, as x approaches pi from the right-hand side, then we know u is going to be equal to the tangent of pi from the right-hand side divided by 2, which we know goes to minus infinity. And when x is equal to 2 pi, then we have that u is going to be equal to the tangent of 2 pi divided by 2, which is going to be equal to, oh, I misspoke earlier, right? So this should be pi over 2, 3 pi over 2. There we go. Yeah, multiples of pi over 2. I was thinking of cotangent for a moment. So tangent of pi is the same as tangent of 0, which is equal to 0. So our integral from before, I'm going to call it star, is going to be transformed into the integral from 0 to infinity plus the integral from minus infinity to 0 of the function 2u over 1 plus u squared, so that's sine, all divided by 2 plus sine times dx. Right? So, therefore, our integral of interest, and we'll deal with this this integral split up in a moment, right? So when can you combine and when can you not? So this integral should not be improper if that is the case. So once I rearrange this, this is just going to be equal to 2u all divided by 2 times 1 plus u squared plus 2u times 2 over 1 plus u squared du, right? So therefore, our integral is the integral from 0 to infinity plus the integral from minus infinity to 0 of u. So I'm going to factor out a 2. So I'm going to pull out a 2 here. So 2 over, because I can cancel, because I can factor out a 2 here, so these 2's can pretty much cancel each other, and I can pull the remaining 2 out if I want to. So that's this 2. And on the bottom, once I sort of distribute things out, I'm going to have u squared plus 1 times u squared plus u plus 1 du. Now I can use partial fraction decomposition on this, right? Now how do I know I can do that? Well, I have two factors on the bottom. It's a degree 4 and the top is less than 4 because the top is degree 1. So once you apply partial fraction decomposition to this integral, you'll realize that this is the integral from 0 to infinity plus the integral from minus infinity to 0 of 2 over 1 plus u squared minus, let's do minus 1 over u squared plus u plus 1 du. Now what do we have here? So the bottom is a quadratic, shifted up 1. And what about the other? So the discriminant of this is going to be equal to b squared minus 4ac, right? Which is equal to negative 3, which is less than 0. So this is also a parabola that's floating above the x-axis. Therefore, there is no singularities for either of these rational functions. Therefore, this integral can be combined using our combination rules for integrals, right? Because there's no singularity at 0 or anywhere in between, so this is not an improper integral, at least of the singularity type. So therefore, my integral can be rewritten as the integral from minus infinity to infinity of 2 divided by 1 plus u squared minus 1 over u squared plus u plus 1 du. So this first integral shouldn't be that much of an issue, and you can complete the square on this second piece if you want. So I can rewrite my integral as the integral from minus infinity to infinity of 2 divided by 1 plus u squared. And for that, I can rewrite as 1 over u plus 1/2 squared plus 3/4. Once I complete the square on u, du. So both of these are arctangent integrals, so I can rewrite this as 2 times the arctangent. Hey, where's my 2 at? I had a 2 earlier, right? Yeah, where'd he go? Yeah, I lost him. There he is. Get back here. Alright, so we have 2 times the arctangent of u minus 2 square roots of 3's arctangent of 2u plus 1 over the square root of 3. Right? And then we're going to send u to positive infinity, send u to minus infinity, and then subtract the limits. So remember that as u goes to infinity, arctangent u goes to pi over 2, and it goes to minus pi over 2 at the other end. So this is going to be equal to 2 times pi, right? So pi over 2 minus negative pi over 2 is going to be pi over 2 plus pi over 2, which is pi, right? And the same can be said about this term. So 2 over the square root of 3 times pi, which we can just rewrite as 2 minus 4 over root 3 pi, right? So what we did was use the Varistor substitution to transform a function of sine and or cosine into a function that is only rational functions. Typically, when you have integrals of rational functions, you will have to use partial fraction decomposition, inverse trigonometric functions, or logarithms in your process. So if you like any of those methods instead of your sine and cosine types of integrals, then the Varistor substitution might be an appropriate choice for your integration method. Hope you enjoyed.